This is an introduction to section 15.4 in which we are looking at collisions. I'm going to introduce some terminology to you now. In figure 15.13, we have objects A and B colliding. A exerts a normal force on B, B exerts a normal force on A. Perpendicular to these forces, we have the plane of contact. We also have the line of impact, which is perpendicular to the plane of contact. This is shown to you in figure 15.13. And for a central impact, the direction of motion of the mass center of each object is along the line of impact. If the direction of motion of the mass center of each object is not along the line of impact, then we have an oblique impact. If you turn to page 269 in your textbook, they have an illustration of an oblique impact in which you have particles A and B coming together and then moving away, and the velocity is at an angle to the line of impact for A and B, both before the collision and after the collision. If you look at the bottom of page 266, they're illustrating different times during an impact. So first we have before the impact, and in this illustration, A and B are moving in the same direction. It is important to use a consistent coordinate system during solving these problems. So if B was moving in the opposite direction, then the sign of the velocity would be negative. So we have positive velocity for A and B in this illustration. But the velocity of A is greater than the velocity of B, so if you wait long enough, these two objects are going to collide. Once they touch each other, the period of deformation begins. During the period of deformation, the mass center of each object is getting closer to the mass center of the other object. And at the instant of maximum deformation, the mass centers are the closest together that they are going to be. And after maximum deformation, the period of restitution begins in which the mass centers are moving away from each other. If you look at A and B together, since each object is exerting a normal force on the other object, and these normal forces are equal in magnitude and opposite in direction, if you look at the impulse from the normal force of A on B and the impulse of the normal force of B on A, these are going to be equal in magnitude and opposite in direction. During the deformation impulse, they call the force P. During the restitution impulse, they call the force R. But it is true by Newton's third law that the impulse would always have the same magnitude but the opposite sign. So when you use the impulse momentum relationship, the net impulse that we have here from the normal forces would be 0. So that gives us equation 1510. If you only know the mass of each object and its velocity before the impulse, then we have two unknowns in equation 1510, so we're going to derive another equation. This equation comes from looking at object A as its own system, and then looking at object B as its own system. In that case, we would have an impulse which is not equal to 0. So this next equation is the initial momentum, this is before the collision, and the final momentum that we have in the collision is at the instant of maximum deformation. So we're going from before the collision to the instant of maximum deformation in this equation. The impulse that we have here is negative because the force that B exerts on A is in the opposite direction to the velocity of A. Then we have a similar equation for going from the instant of maximum deformation to after the collision. And before the instant of maximum deformation, we're calling the normal force P. After the instant of maximum deformation, we're calling the normal force R. Then we can do the same thing with object B, going from before the collision to the instant of maximum deformation and using the impulse momentum conservation law. and then going from the instant of maximum deformation to after the collision, and that gives us another equation. We're going to take these two equations, and from that calculate the coefficient of restitution. The coefficient of restitution is the ratio of the restitution impulse to the deformation impulse. And doing that for our equations that we had from looking at object A, we get this here. Then we do the same thing with the equations that we have from looking at object B. We want to get rid of the velocity v, which is the common velocity that the objects have at the instant of maximum deformation when they are moving together. And so we can solve these two equations to get rid of v. And if you want to see the math for that, that is over here on the side. But in the end, we get equation 1511, which is shown here. On the next page in your book, they talk about elastic impact and plastic impact, or another name for plastic impact is inelastic impact, or as we call them in Physics 161, elastic collisions and inelastic collisions. In perfectly elastic collisions, the deformation impulse is equal and opposite to the restitution impulse, and by the equation we saw on the previous page, that means the coefficient of restitution is equal to 1. They tell you in the book that in reality this can never be achieved for an elastic collision, and that's because if you turn to page 266, it says the physical properties of any two bodies are such that the deformation impulse will always be greater than that of the restitution impulse. It is possible for subatomic particles to have perfectly elastic collisions. If you have macroscopic particles, you can never get a perfectly elastic collision, but you can get close to a perfectly elastic collision. And a collision such as one between steel balls, which are very hard and so do not deform much, would be close to a perfectly elastic collision. In contrast to that, we have inelastic collisions where the coefficient of restitution is equal to 0. If the coefficient of restitution is equal to 0, that means that the restitution impulse, which is the numerator in our ratio for the coefficient of restitution, that restitution impulse must be equal to 0. This means that the objects stick together after the collision, and so they continue to move with a common velocity. In an inelastic collision, we are losing kinetic energy to thermal energy, sound, and deformation, and you can read about that on the bottom of page 268. And you should be reading all of section 15.4. And when you finish that, we'll be ready to solve some example problems.